Good day everyone. In this video, you will learn on how to calculate the magnetic field in a moving single charge particle and also the electric field simultaneously. Before going into this topic, let us recall first the principle of electrostatics, wherein the principle says that for any stationary charge placed in a space will generate or distribute the so-called charge distribution. Now, it is outward if the stationary charge is positive, while inward for a negatively charged, which means that uh, at any point in the surrounding space, the stationary charge generates electric field at any point. So, for example, if we have point P located at the distance r from the source charge, then electric field can be found at that point. And this electric field is outward because the charge is positive. Because all positives, the distribution is outward. The direction of distribution is also the direction of the electric field, which means that for negatively charged, the electric field is inwards or towards the charge. It's because of negatively charged. Now, according to theory, that the electric field is directly proportional to the magnitude of the charge, meaning the greater the charge of the stationary charge, the greater the electric field. But it is inversely proportional to the square of the distance from the source charge, which means that in a faraway distance, the electric field is approximately to zero. As the distance increases from the source charge, the electric field is keep on increasing until approximately zero in an infinite distance, while the electric field is maximum at the surface of the charge. Now, to calculate the magnitude of the electric field, it is equivalent to 1 over 4 pi permittivity, we call this as the electric constant, multiplied by the magnitude of charge divided by the square of the distance. Now, for the electric field vector, we just multiply the magnitude by the direction of the electric field, which is r hat. R hat represents the direction of the electric field. Now, the unit of this electric field is Newton per coulomb, or sometimes we call this volts per meter as the unit for the electric field. The electric constant, or 1 over 4 pi permittivity, is equivalent to 9 times 10 raised to 9 Newton meter squared per coulomb squared. So therefore, in order to calculate the electric field, we just only need the magnitude of the charge. This stationary charge, then we need also the distance from that stationary charge. Then the magnitude of electric field can be calculated. And its direction is outward for positive, inward for a negatively charged. Now, in the case of the magnetic field, in the area of magnetism, in similar way, if the stationary charge generates electric field, the moving charge generates magnetic field. Okay, so if we have, let us say, a positively charged, whose magnitude is Q, travels in the direction towards B, or the velocity V, then there must be a magnetic field. Because for any charge having a velocity, meaning it is a moving charge, there is always a magnetic field, which means that in opposite way, if the charge is stationary, meaning not moving, magnetic field is zero. But the electric field, while the charge traveling, there is always an electric field. Because regardless whether it is stationary or moving, electric field is present in the surrounding charge. So in this case, let's focus on the effect of the moving charge as a result of the magnetic field. So suppose we want to know how much magnetic field at a certain point P, the distance R, then the magnetic field, this is always normal to the plane generated by the velocity direction and its position vector. Okay, so therefore, in the angle between the velocity direction and R provides a plane, and that plane, normal to that plane, is the direction of the magnetic field, which means that this is a kind of a three-dimensional situations, because the magnetic field is always normal to the plane generated by the velocity and its position. So therefore, in that case, the magnetic field is perpendicular to that plane, the shaded one. Now, this magnetic field follows the right-hand rule, which means if you curl your fingers while stretching your thumb, the direction of your thumb is the direction of the velocity, and the curl of your fingers, the four fingers, remaining fingers, will be the direction of the magnetic field. So in that case, for the magnetic field at point P, the magnetic field is normal to that plane. Okay? So therefore, that is the magnetic field. By principle, the magnetic field is similar to electric field, which is directly proportional to the magnitude of the charge, which means that the greater the charge, the moving charge, the greater the magnetic field. And also, in similar way in electric field, it is also inversely proportional to the square of the distance of the point from the source charge. But, different from electric field, the magnetic field proportional also to the velocity, the sine function times the velocity is also proportional to the magnetic field. Now, the V sine P is actually the normal distance of velocity, or the perpendicular distance of velocity away from the plane, or the point P, which means it is the shortest distance, which means in order to provide a magnetic field, take note that it is normal to the plane, so we need the perpendicular distance. So that is the velocity, or the magnetic field is proportional to the also to velocity sine P. Now, to calculate the magnitude of this magnetic field, we know already the direction by right-hand rule. The magnitude is equivalent to mu naught over 4 pi. This is called as the magnetic constant, multiplied by the magnitude of the charge, meaning if it is negative, remove the negative, consider the positive, then multiply it by the V sine P, where the V is the magnitude of the velocity and P is the angle between the velocity towards the position vector. The position vector is a line that connects from the moving charge towards the point of interest, and divided by the square of the position magnitude, R squared. So therefore, we can say that the magnetic field magnitude can be calculated if we have the charge magnitude, the velocity, and the position of that point, meaning the point where we want to know how much is the distance of the point from the charge towards the point of interest. So that's it. Now, for the magnetic field vector, the magnetic field vector is the product of the magnetic constant, or mu naught over 4 pi, multiplied by the charge. Now, this we have to consider the charge, meaning if it is negative, give it negative. If it's positive, give it positive. Then multiplied by the cross product of the velocity vector to the unit vector r hat. The unit vector r hat is the direction of away from source charge, from the moving charge towards the point of interest. Then divided by the square of the magnitude of the position vector. So that's it. Okay. Now, recall that the unit vector is a vector that has a magnitude of 1 is equivalent to the position vector divided by the magnitude. So if we want to know what is the unit vector, then just divide the vector itself and its magnitude. And the result is the unit vector. Then give it to the formula in order to calculate for the magnetic field. Now, we have also an optional, or we have also other formula for the magnetic field vector. This is where we substituted the unit vector. We substituted the unit vector calculated in this part to this formula. Then the result is the magnetic field is mu naught over 4 pi multiplied by the charge and the cross product. Now this time, this is the cross product of the velocity and the vector, position vector, not the unit vector. But this is divided by the cube of r. Remember, this becomes cube because we multiply that with another r to the r squared. So we can use any of this formula for calculating or providing the magnetic field vector. But the magnitude of the magnetic field is just equal to the magnetic constant and the absolute value of the charge v sine p, where p is the angle between the velocity and the position divided by the square of the distance of the point of interest. That's it. Okay. So again, reminders that there are two ways to provide the direction. We can use the right hand rule or you can use the formula. The magnitude can be calculated using this formula. Okay, so this law, we call this as the Biot-Savart law. We're able to provide the calculations of the magnetic field for the given charge. It was the Hans Christian Ørsted that there is always a magnetic field for a moving charge, for a charge. Then it was the Biot-Savart provides the mathematical calculations of that magnetic field. And we will be using this one if you are asked to solve for the magnetic field generated by the moving charge or maybe moving charges. Okay, so again, because this is the magnetic field is curling about the direction of the velocity, then it follows that this plane, which is we constructed before, will rotate about the axis, where the axis is the direction of the velocity, then it will rotate. Meaning whatever velocity, whatever magnitude at point B, have the same magnitude as this plane rotates about the direction of the velocity. So therefore, it will rotate around that axis and it has the same value of the magnetic field. So therefore, because the magnetic field is inversely proportional to the radius, which is perpendicular to the point of interest, then the magnetic field at exactly in the direction of the velocity is 0. So this is 0. Why? Because if you look at the formula, the cross product of the velocity and position now, the angle in between the two is 0. So the cross product of the same direction is 0. Okay? So again, if we move this point closer to this charge, this magnetic field becomes greater and greater. Because the closer, the greater, the farther the distance from the charge, the smaller the magnetic field. Okay, so if we have this observer looking at the direction of the velocity while traveling away from the eye of the observer, then looking at the magnetic field that surrounds the axis or the direction of the velocity, this will be the result. Which means that at the center of this is the direction of the velocity which is moving away from the eye of the observer. And this one are the curling velocities of the curling magnetic field, which have the same magnitude. They have the same magnitude because they have the same distance. If they have different distance, then different magnetic field happens. But in this case, the magnetic field curling with the same magnitude around the direction of the moving charge. Now, the mu naught means the permeability of the vacuum, the ability of the magnetic effect that penetrates to the vacuum area. Where the magnetic constant, which is mu naught over 4 pi, is just equal to 10 raised to 7 Tesla meter per ampere. So therefore, if you are using this formula, then you need the value for mu naught over 4 pi, just use 10 raised to 7. And that is equivalent to mu naught over 4 pi. Okay, so to apply the formula that we presented, let us solve this problem. The problem number 1 says that 6 microcoulomb point charge is moving at a constant 8 times 10 raised to 6 meter per second speed in the direction of the positive y direction. So we have this charge. The magnitude of the charge is 6 times 10 raised to, and this is a positively charged microcoulomb. This is traveling towards the positive y direction, whose magnitude of the velocity is 8 times 10 raised to 6. So therefore, the velocity vector is just equal to 8 times 10 raised to 6 j hat, because this is directed towards the y-axis. Okay, then according to the problem, at the instant when the point charge, because the charge travels along y direction, positive y, at exactly at the origin, taking the snapshots at that point, where the observer says that the charge is exactly at the origin of the Cartesian, or the frame of reference. The question is, what is the magnetic field vector it produces at the point whose coordinates are x is 0, y is 0.5 meter positive, z axis is 0.5 meter also. So in this case, x is 0, so there's no component of the position point along x. So it is only line along the x the yz plane. So therefore, the y is 0.5. So measuring from this point towards this point is just 0.5, and moving here is 0.5 also for this. So therefore, the coordinate of the point P is 0 for x, 0.5 for y, positive 0.5 for z. This is our point of interest, and we want to know how much is the magnetic field at this point experienced because of the moving charge, which is exactly at the origin, at a certain instant only. Okay, so therefore, the position vector is a line that connects from the origin, which is the location of the charge also, towards our point of interest. Take note, this is a plane. The plane is xy plane. We don't have plane in x because x is 0. Now the question is, how much magnetic field produced because of the moving charge? So remember that we have the area, and perpendicular to this area is the magnetic field. Okay, if we apply the right hand rule in this configuration, take note that this plane will rotate about the y-axis. This will rotate about the y-axis, which means that the magnetic field is tending to rotate in what? In a clockwise direction, in the counterclockwise direction of y. So it will rotate, this will rotate towards y. And the magnetic field is the same while this plane rotated. But our question now is, how much is the magnetic field at this point? That's it, no? So, we have already the idea that this is about the direction using the right hand rule, that this magnetic field is directed towards x. This is using our right hand rule. Now the question is it agrees the theory using the formula? Let's find out. So our question at our task now is to calculate the magnetic field vector. So therefore, we have to present this with magnitude and direction. Okay, so the formula to be used is this one. The magnetic field is equal to mu naught over 4 pi q, the cross product of the velocity vector with the unit vector, divided by r squared. So in order to calculate this magnetic field, which we want to know, then we need these values. Mu naught over 4 pi permittivity, nothing to worry because it is 10 raised to 7. Charge is given as, the charge is given as 6 microcoulomb. So convert this to SI, becomes 6 times 10 raised to, times 10 raised to negative 6 for the charge. Then this velocity, v velocity, is just equal to 8 times 10 raised to 6, and this direction is j hat. So j hat. And the position vector, we will calculate this because the position vector is from the charge towards the point of interest. And we have this component. So we will provide the vector, position vector, then divide it by its magnitude. And this is it. We can provide the unit vector. And substitute everything here. And the result will be our magnetic field. Okay, let's do it. So first is, the position vector based on the given is 0.5 j hat, only 0.5 k hat for the z component. There's no x component, so there's no I hat here. So we have only the vector in terms of j hat and k hat. So we have already this vector. Then the magnitude of this, take note, is just the square root of the squares of the magnitude of the component of the position along y and z only. So square of 0.5 plus the square root of 0.5, take square root, and this is the magnitude of the position vector, meaning the distance from this charge or the origin towards this point is 0.707 meter. Okay, so again, we need the unit vector. So the unit vector now is the result if we divide this vector, position vector, by its magnitude. So 0.5 j hat plus 0.5 k hat, divide everything by 0.7. The result is 0.707 j hat plus 0.707 k hat. This is our unit vector. Remember, unit vector is a vector whose magnitude is 1. So if you want to verify if this is 1, then take square root of this, square 0.7, square 0.707, then add, take square root. The result is approximately equal to 1. So therefore, this is our unit vector. Now, substituting all of this to the formula. Remember, mu naught over 4 pi is just 10 raised to negative 7. And this 6 times 10 raised to 6 is our charge, which is Q. Okay. Then V, velocity V, vector, is 8 times 10 raised to 6. So this is our velocity vector. And we need to cross this with our position vector or unit vector, 0.7 times 0.707 j hat plus 0.707 k hat. And everything divided by the square of the magnitude of the position, which is 0.707 squared. Okay? Now, simplifying this, remember in algebra, we need to distribute We need to distribute this each term. But inside this grouping symbol, we need to distribute it again. So we will distribute this taking the cross product. So we have 0.8 times 10 raised to 6 j hat cross 0.707 j hat. Remember, j hat cross j hat. The same direction, the cross product is 0. So therefore, this term becomes 0. So there will only survive term is only 8 times 10 raised to 6 multiplied by 0.707 k hat. Now, so therefore, we have j cross k. Okay? So, multiply that with this value. This is the result. Okay. We have 10 raised to 7 as is, 6 times 10 raised to 6, times 10 raised to 6. Then the quantity inside this bracket is 0 because this is j hat and j hat. Then plus this one, which is 8 times 10 raised to 6 times 0.707. Then we separate the unit vector by j cross k. Now, remember, j cross k is I hat, which means that simplifying this one, multiply this, we're gonna divide it by 0.707 square, and the result is 6.79 times 10 raised to 6, negative 6 Tesla, and this is I hat. I hat because this is j cross k. So the result of the theory, the theoretical result, the magnitude is 6.79 times 10 raised to 6 Tesla in the direction towards positive x-axis. So you compare that in our right-hand rule, it is true that the magnetic field is directed towards positive x-axis. So this is the solution to the problem presented in problem number 1. Okay, next problem. Problem number 2. In the Bohr model of hydrogen atom, the electron moves in a circular orbit of radius 5.3 times 10 raised to 11 meter with a speed of 2.2 times 10 raised to 6 meter per second. These are given to the problem. If we are viewing the atom in such a way that the electron's orbit is in the plane of the paper with an electron moving clockwise, find the magnitude and direction of the electric field and magnetic fields that the electron produces at the location of the nucleus treated as point. Meaning, we don't care about the charges inside the nucleus. We just consider only the point. So, this is a very challenging problem because we are required to calculate the electric field and also the magnetic field. So, we need two answers. And this is the combination of electrostatics and magnetism. So, problem says that we have this electron charge. Remember, electron charge is a positive and negative charge. This orbits around the nucleus, in this case. The location of the nucleus is the center, the circle, while the electron travels in a clockwise with a velocity magnitude with a constant speed of 2.2 times 10 raised to 6 meter per second. The radius of this orbit is 5.3 times 10 raised to 11 meter from the nucleus. Okay, so we need to provide the magnetic field, electric field, and also the magnetic field. Now, this is the location of the nucleus. We ignore the charge. The nucleus, we need to consider only the electron charge. And this is the electron, or the orbiting electron. Okay, so we need this R, or the R, using the idea of the electric field. The electric field is towards the charge because the charge distribution is inward because of the negatively charged. So, theoretically, the electric field produced by these electrons in the location of the nucleus is towards the electron. Okay? So, and the magnetic field is towards the plane. Why? Because if you use the right hand rule, curling your fingers, stretching your thumb is the direction of your velocity, and the curling is one of the fingers. So therefore, it tends to move towards the plane. That's why the magnetic field, I have this X. X signifies that the magnetic field is moving towards the plane. So we will now calculate the magnitude and direction of this magnetic field. So these are just the right hand rule for the magnetic field and the principle of distribution, negative distribution, positive distribution for the electric field. So let's calculate first the electric field. So we will be using this formula, the 1 over 4 pi permittivity Q over R squared. Okay, but remember 1 over 4 pi permittivity is just equal to 9 times 10 raised to 9 Newton meter square per Coulomb squared. This is what we learned in electrostatics. Then, substituting the values, this is for the electric constant, and this is the absolute value for the electron charge particle, and this one is the center, or the distance, or the radius of the point of interest from the nucleus towards the electrons, which happens to be the radius of the circle. So this is 5.3 times 10 raised to negative 11 meter, then square it. Okay, simplifying, the result is 5.13 times 10 raised to 11 Newton per Coulomb. This is the magnitude of the electric field, and the direction is towards always the electron. Meaning, as the electron travels around the circle, the electric field is always directed towards that electron. Okay, now, for the magnetic field, we will be using this formula for the magnitude of the magnetic field. Mu naught over 4 pi, the absolute value of the charge, V sine P, and the square of R. So, take note that the mu naught over 4 pi is just equal to 10 raised to negative 7. And the charge is the same, 1.602 times 10 raised to 910. The velocity is given as 2.2 times 10 raised to 6 meter per second. It's already SI. Remember, take note that when we use the formula, make sure that the units are consistent. So all of these are in the consistency of unit in SI. So therefore, we just substitute it here. Then the angle between R and velocity while rotating around the circle is always 90 degrees. The reason is this velocity is always tangent to the curve. So therefore, it is always perpendicular to the radial axis. Okay, so this should be 90. Divide by R, and R is just equal to 5.3 times 10 raised to negative 11. Okay, substitute everything. Again, this is for the magnetic constant, the charge, absolute value, disregarding negative, 2.2 for the velocity, times 10 raised to 6. Sine of 90 is 1, divided by 5.3 times 10 raised to negative 11. Square it, then simplify. And the answer is 12.55 Tesla. This is the magnitude. The direction is, we use the right-hand rule. It is always towards. While the electron travels around the circle, the magnetic field is directed towards the plane. Okay, so that's all for today. Thank you for watching.